Hello, students. This screencast is about the Fundamental Theorem of Dilations. The document is in modules under reference. And we're not going to spend class time on it, but I thought it was useful to go through. It's an interesting theorem, and it is really fundamental for dilations. It's, as it says in this first sentence here, it's foundational to the work of dilations and similarity. We don't have to worry about what the Common Core says. The proof uses the fact that the opposite sides of a parallelogram are equal, which you know. So it says, it's clearly the case that if you have a segment from C, the center of dilation, to some other point, then under a dilation, it maps into a collinear segment, and the length gets stretched by the scale factor. That's clear. But if C, A, and B are not collinear, in other words, if A and B are not collinear with C, so you have some arbitrary segment, then it's also true, almost also, that the image of the segment AB under a dilation is stretched by the scale factor as well. That does not follow from the definition. And also, it's parallel. So it won't be collinear this time, but it will be parallel. And as I said, the last sentence says, if they are collinear, then it's what I just said. Okay, so there are two parts to the theorem. The first part is the parallel, and the second part is the stretch factor. The parallel part, and I did these proofs. You might. I haven't seen them anywhere else. The parallel part is remarkably easy. We show that under a dilation with center C, so C is the center, and scale factor K, the image of a line not through C, so AB, must be parallel to its preimage. And given a dilation, assume that the image of line M is M prime here. And suppose it's not parallel. This is an indirect proof, which I know you covered either in geometry or in advanced math topics. Advanced abstract math, which you did in the fall, some of you with Dr. Fitzpatrick. So we assume that they're not parallel, so they have to meet at some point. And choose some, suppose that point is B, where they meet. So B equals, B is the point where the image meets, and that means that B prime has to equal B. We'll do that in a second. So choose another point A, not on M. Okay? The image of A is the intersection of line CA, because it's on the same line, with line M prime. And B prime has to equal B because it has to lie on M prime, and it also has to lie on CB. And the only point that does that is B. So what that means is from A and A prime, if you just look at A and A prime, the scaling factor has to be bigger than 1 because it stretches, or less than 1, but it's not equal to 1. But from B and B prime, it's not equal to 1, yes. And from B and B prime, K equals 1. But that's it, because the scale factor is a constant. So that's the story. So M, if M passes, so then the other part is what I talked about. So they can't be parallel. If CAB they must be parallel, They must be parallel. So the image of any segment must be a parallel segment if the segment is not collinear with the center of dilation. Okay, part 2 is a little harder. We show that under a dilation with scale factor K, the length of the image of any segment is K times the length of the preimage. Okay? So let A prime B prime be the image of AB in a dilation of center C. So A prime B prime, this bottom segment of the triangle, is the image of AB, and we know it's parallel. Okay? All right. And scale factor K, with the lengths of the various segments labeled in the figure. So length A, length C, length E, length B, length D are all labeled. Okay, then, okay, K, the scale factor, is A plus B divided by A. That's the definition of the scale factor from C. And C plus D over C must also be equal to K. All right, so here is, now we go down to the second diagram, okay? By part one, AB and A prime B prime are parallel. So draw a line through B, a line through B parallel to AA prime. So AA prime is this line, and we're going to draw a line through B parallel to that line. All right, and let this line intersect A prime B prime at K. That's here. Now, dilate triangle ABC, right here, ABC, from center B this time. So this is different. Now we're doing it from center B instead of center C. Okay, with scale factor, and this proof relies on the use of a negative scale factor. If you don't allow that, you can't do this. But we talked about negative scale factors being okay. So the scale factor is going to be minus D over C. Minus D over C. Okay? And that results, as you know, a negative scale factor means it stretches in the opposite direction. So, resulting in the figure that's shown. So the image of A under this dilation is going to be A prime. The image of C has got to be B prime because of the choice of scale factor. Okay. And so we have parallelograms because AB is parallel to A prime B prime, and we made BK parallel to AA prime. So this is a parallelogram, which means that A prime K has to equal E. Okay? And also, let's see. That's right. Segment AC has to map into a parallel segment because dilation takes a segment into a parallel segment if it's not collinear with the center. So that means A prime B prime must also be parallel to AA prime. And that means that A double prime, B prime, A prime is also a parallelogram, which means that the opposite sides are equal, so A double prime, B prime has to be B as well. So that's the new labeling. And also, B, A prime, B prime, K is a parallelogram because the opposite sides are parallel. So K, B prime must equal B, A double prime, which is F. So I labeled those lengths in the figure, okay? So by the definition of dilation, the length D over the length C has to be the same as the length F over the length E. They're stretched by the scale factor. So if we add 1, now we do a little algebraic little trick here. We add 1 to both sides of that equation and get a common denominator. So you get that C plus D over C is equal to E plus F over E. Okay? Okay. So in terms of segments, this translates to C plus D is segment B prime C, which is C plus D, B prime C, this side of the triangle, over BC, which is C, is equal to E plus F is A prime B prime. A prime B prime is E plus F, divided by E, and one representation of E is AB. Okay? But that has to equal, let's see, because A prime B prime over AB, A prime, yes, A prime B prime, oh, I'm sorry, B prime C is the long leg here. B prime C over BC is the original scale factor K that we used from point C. So therefore, A prime B prime over AB has to also equal K, which means that A prime B is K AB, as was to be proved. Okay? And then it says if they're collinear, the case is easier, just based on the distributive rule. So this is the hard case. Okay, and so just to wrap up, similar triangles. That means a corollary of this is that since every segment gets mapped into a segment that's parallel, that means similar triangles must have equal angles. If in other words, if one triangle is an image of another under a dilation, then since the image segments will be parallel to the pre-image segments, the angles must be preserved. So that's an important, that just from the parallel part, well, not the parallel, that also, well, yes it is, just from the parallel part. You get that similar triangles have equal angles. The proportional sides follows from what we just did. Because when you do a dilation, any side gets stretched by the same factor. Any segment doesn't have to be collinear with the center. And here's a quick proof. Every isometry preserves side lengths and angle measures because similar means a combination, a composition of isometries and one or more dilations. One is enough. A dilation preserves angle measure because the image of any segment is parallel or collinear with its pre-image. So a dilation also preserves ratio of sides because the length of every segment is multiplied by the fixed scale factor. So this completes the proof. And it also completes the screencast. Thank you. I just need to return to it. Let's see, where is it? Here. All right. Jeez. There. Had to get it back.